Welcome back, anatomy scholars. My name is Amalia, and today we are going to be learning about the cardiovascular system, also known as the circulatory system. And we're going to be basing our lesson off of Victoria's beautiful study guide that we have right here. So, the cardiovascular system includes mainly the heart and the blood vessels that we're going to be talking about later on. So you can definitely say that the heart is the heart of the cardiovascular system. So the main function of the circulatory system is the transportation of blood. So we'll see that through vessels and through the heart itself, we're going to be transporting blood all throughout the body. And it is a closed transport system, which means that the blood stays confined to blood vessels. It's going to mainly stay within the heart and the blood vessels. No, it is going to solely stay within the heart and the blood vessels. We do not want blood anywhere else in the body. If it is, say that it's leaking within the thoracic cavity, that would be very, very dangerous, and I would definitely hope you go to the hospital. That is not okay. But we are going to be learning about the circulatory system, and we're going to start off with the heart. So, the heart, I'm pretty sure you've heard this, but it is about the size of your fist. If you close your fist and kind of put it a little left of the center of your chest, that's roughly the size and location of your actual heart. It's about 1 pound in weight. This weight may vary depending on whose heart it is. It is located in the thoracic cavity, basically where the lungs are and where other vital organs are, which are encased in the rib cage. So that's basically where your thoracic cavity should be. And it is flanked by the lungs, like we said before, and it rests on top of the diaphragm. So the diaphragm is roughly at the bottom of your rib cage, and it makes sure that your lungs are exhaling and inhaling. When you do exhale and inhale, the diaphragm is aiding you in that process by pushing carbon dioxide out of the lungs and relaxing so that way you can take oxygen in. The coverings around the heart are the pericardiums. So they're wrappings, coverings, and a membrane that surrounds the entire heart. So now we're going to go into specific coverings. We have the visceral pericardium, also known as the epicardium, and it is the inner layer membrane that tightly hugs the external surface of the heart. And it's actually part of the heart wall itself. So when you go into the specific study guides and learn about the heart walls and the heart linings, you'll see that the epicardium is the external layer of the heart. It basically hugs the heart. It prevents the heart from rubbing against other organs as it pumps blood and moves. So that way everything functions smoothly. It also acts as an insulating layer, so that way the heart is also protected. Now we have the parietal pericardium, which is right here, and it is the outer, looser layer that anchors the heart to surrounding structures. So usually with the pericardium, you will see this in other systems as well. It basically connects organs to the surrounding organs or the surrounding bodily cavity to ensure that everything stays in place. And between these two coverings is a slippery fluid that prevents friction between the layers as the heart beats. So this pericardium and the parietal pericardium are going to have a fluid in between them to also prevent friction, as we had discussed before. Now the heart wall structure. There's the epicardium, like we had discussed here, and it is the outer layer of the heart wall. We have the myocardium, which is the middle layer. Think middle. And it consists of the cardiac muscle tissue, which we will be contracting with when we talk about the purpose of atrium and ventricles later on. And then the endocardium, endo meaning in, that's a good way to remember. It is the inner layer, and it is a thin, glistening sheet of tissue that lines the chambers. So this continues with the linings of the blood vessels, leaving and entering the heart. So when we talk about the blood vessels in a little bit, you will see that the endocardium is basically inside the heart, and it ensures that everything is flowing smoothly, a little protection so that way inner erosion of the heart also doesn't occur. Now we have the heart chambers. You have probably heard of this if you have studied anatomy before, but we have the atria and the ventricles, and there's two of each. The atria is known as a collecting chamber that collects blood within the heart. So you'll see this is an atria, the left atrium, and this is the right atrium. And depending on which side of the heart that the atria are located, there will be either oxygenated blood or deoxygenated blood. And the same thing goes for ventricles. And the ventricles are very, very muscular chambers, so that way they can pump out blood to the rest of the body via blood vessels. And then we have the septum, and it separates the right and the left sides of the heart. And so your septum is going to be right down here. And so this is also known as the muscular pump, as we talked about before. Since the lower portion of the heart is very, very muscular, it helps to pump blood throughout the entire body upon one pump of each ventricle. Heart valves. So the heart valves help prevent the backflow of blood. So you will see that the valves are located over here. There's one over here, one over here. And they're located at the atrioventricular area to ensure that backflow doesn't occur over here, and at the entrance of each vessel. So there are 4 total within the heart, and as we had talked about before, the atrioventricular valves, which are located between the atrial and ventricular chambers on each side, ensure that no backflow occurs. And in fact, if you ever listen to someone's heartbeat using a stethoscope, you will hear that a regular heartbeat goes boom, 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 or thud, thud noise. When one of these valves aren't working or any of the valves in the heart are not working, you will hear a swish sound. And that swish basically indicates that there's backflow occurring within the heart, which can be very, very detrimental to someone's health. So knowing that, we know that these valves have a very, very important purpose that cannot go unnoticed, even though they're very, very small, as you can see here. So these are the specific atrioventricular valves, which are very specific to each side. We have the left AV valve, and we have a right AV valve, which are specific to the terms over here if you want to look into that. Now that we talked about the atrioventricular valves, we are going to move on to semilunar valves. The semilunar valves guard the base of 2 large arteries leaving ventricular chambers. So as we had discussed before, the ventricular chambers are very, very muscular segments of the heart that pump out blood to the rest of the body. When we have the semilunar valves, these valves are going to prevent the backflow of blood from these very muscular chambers and ensure that all the blood is going in the right direction. And these are the side-specific semilunar valves that we will have depending on which side that the valve is located on and if it is dealing with oxygenated or deoxygenated blood as a result. And now we have the chordae tendineae, and this is going to be the tiny white connective tissue attached to the inferior side of each leaflet, and it anchors the flaps of the valves. So that's going to be right here, and as you can see, it anchors the flaps down to the sides of the heart. So this connective tissue, if you've ever dissected a heart in a lab before, you will see it almost comes across as like stringy, and it will be just connective tissue for the purpose of holding these pieces of the heart together. And specifically, it would be the flaps for this portion on each side, as you can see here, and that is the chordae tendineae, all in here. Now we have pulmonary and systemic circulation. So pulmonary basically means related to the lungs. We're going to see how big of a role that the heart and the blood vessels play within the respiratory system and discuss its use with waste and oxygen. So pulmonary is the right side, and it serves as a pulmonary circuit pump. Basically, it will flow between the heart and the lungs to either dispose of waste to the lungs that we can exhale or collect oxygen that it can bring back to the heart to pump to the rest of the body. And then we have systemic circulation, which is the left side, and it serves as a systemic circuit pump. And the blood will flow between the heart and the rest of the body. So this side is going to be oxygenated blood, as the oxygen needs to be transported to the rest of the body via a major blood vessel. Now we have the blood vessels. So our blood vessels that we will have, and it will only be these three within the body, are the arteries, the veins, and the capillaries. These each have a distinct shape, a distinct look, and a distinct role and function within the body. So we're first going to talk about the arteries. So the arteries are the blood vessels that carry blood away from the heart. To remember that, you can definitely link that A in arteries with away. So A and away from the heart. And these you will see are our largest blood vessel for the purpose of blood being pumped into it by the ventricle, which is a very, very strong muscular chamber. A specific artery that we can talk about is the pulmonary artery. And you can see that it carries the oxygenated blood away from the right ventricle towards the pulmonary capillaries around the lungs. We will discuss the function of capillaries a little later in this video, but basically the artery will be just for transportation, and it will transport deoxygenated blood away from the right ventricle, as we see it stems from a ventricle, which is why it's an artery, to the pulmonary capillaries around the lungs, and these capillaries will dispose of any waste or carbon dioxide that is within these blood vessels and collect new oxygen and nutrients. Now we have the aorta, and this is, you will usually know as one of the main blood vessels in the body. It is the largest artery, hence why it's so important, and it carries oxygenated blood away from the left ventricle to systemic circulation throughout the whole body. So what this aorta is going to be doing, it's going to be providing oxygen and nutrients to every single part of your body, and it's going to be doing this via systemic circulation. So if you've ever seen a show of Grey's Anatomy or any hospital-related show, if anyone gets severely injured and injures their aorta, you will see that the blood that's being pumped through the aorta will come in spurts and surges. Since the heart is beating to contract and push out blood through the ventricles, you will see that the aorta is receiving surges of blood. Hence why if someone were to ever severely injure their aorta, blood will come out in spurts. So these arteries are very thick-walled because they are getting blood from the ventricles, which is very, very strong surges. So they need to be very muscular to handle that pressure. And so it's a very thick muscle layer, and they're very elastic and flexible for that reason. They're located very deep within the body, and they have very high pressure spurts, as we discussed before, which is why they're thick-walled and have thick muscle layers, and there are no valves present within the arteries. Now we have veins. Victoria very smartly put veins in blue for a reason. If you look at your wrist, you can actually be able to view some of your veins. They may appear blue or green depending on your skin tone, but you can view them on your wrist through your forearm area and all the way up to the smoother area on the other side of your elbow. So veins are blood vessels that carry blood back to the heart. Now we have specific veins that we are going to talk about that you can refer to. So we have the vena cavas, there's two of them, and they both return deoxygenated blood from around the body cells to the right side of the heart, which we had talked about collects the oxygenated blood. So there's the inferior vena cava, and it returns blood from below the diaphragm, basically anything from like your waist and underneath, so your legs, your feet, and a little bit of your torso. And the superior vena cava returns blood from above the diaphragm. So you're going to have your thoracic cavity and your head, which is very, very important. Then we have the pulmonary veins. The pulmonary veins are veins that return oxygenated blood from the pulmonary capillaries around the alveoli in the lungs to the left side of the heart. Now, the pulmonary veins are going to be very important because they are the reason why in your heart you are going to have oxygenated blood. So, they're going to take the oxygen that they have received from the alveoli in the lungs, and they're going to transport it all the way back to the heart, to the left side of your heart, to your left atrium, so that way it can be transported to the rest of the body. Now, veins are very thin-walled, and there's very little muscle. So if you've ever looked at the cross-section of a vein, you're going to see that it takes on a very collapsed-looking flat shape, and that will differ from the rounder artery cross-section that you will see. And since it doesn't have to receive any blood from ventricles, it will not be thick-walled, and it is not elastic. It's closer to the surface, so you can view them on your forearm or your legs, places like that. Valves are present in these veins, and there's very low pressure since they are not receiving blood from ventricles. Now we have the capillaries, and the capillaries are going to be the vessels that take more of a part within the respiratory system. So let's get into that. So capillaries are blood vessels that connect small arteries, also known as arterioles, to small veins, venules, and they are thin-walled to allow for diffusion of gases, nutrients, etc. So when we are making something smaller, in the medical field or in biological terms, we always put an ol at the end. Just like in Spanish, you can put an ito or an ita to make sure that the other person knows that you're talking about something small. Within biology, we make ols that indicator. So these capillaries will basically be very, very, very small, so that way they can ensure the diffusion of gases, nutrients across their walls. So they are very, very thin-walled, one cell layer thick to allow for this diffusion. So you will see that they are surrounding the little grape-like structures within the lungs, which collect oxygen and carbon dioxide or waste. And the capillaries will either take that oxygen from the alveoli, so that way it can be transported to the heart, so that way the oxygen and the nutrients can be transported to the rest of the body. So these capillaries are too thin, so they do not have muscle, they are not elastic, and there are no valves. And they're located throughout the body. So if you see over here, these are very, very small capillaries, also known as a capillary network when they're bunched together. So basically, as arteries or veins near the lung area, you will see that they become smaller and branched off into arterioles and venules, so that way they can branch off into capillaries to collect or deposit nutrients or gases. Now, the anatomy of blood vessels. So basically the makeup that we see over here is going to be discussed right here. So we have the tunica, which lines the lumen or the interior of these vessels, which you'll see right here, and it consists of a thin layer of squamous epithelial cells, and the cells fit closely together and form a slick surface. So for the arteries that we see over here, the lumen inside will be lined by the tunica intima, and this will prevent any friction and very, very slick walls, so that way blood is transported very, very, very easily. If you ever build up your cholesterol, or if you ever build up cholesterol or fat within your body, it lines these walls, and it will be a lot harder for blood to get through your vessels. And we have the tunica media, which is the bulky middle coat, which is right here, as discussed in the diagram, and it is mostly smooth muscle. So it is involuntary, we cannot control it, and unstriated. So the tunica media also lends to the structure of each of these vessels that we see over here. And then we have the tunica externa, and is the outermost tunic, and it's composed of fibrous connective tissue that supports and protects the vessels. So it is more of a support system for these vessels, so that way they do not collapse upon themselves, and they protect the vessels, and they also connect them to surrounding tissue or surrounding organs. Now we're going to have electrical conduction of the heart. So Victoria very smartly put these lightning bolts right here for us to indicate that certain terms that she may be using apply to electrical conduction of the heart, or that they're electrical themselves. So if you see that in any of the study guides in the file folder, you will see that these lightning bolts indicate that. So with electrical conduction of the heart, you will see that this pertains to the rhythmic beating of the heart, and basically pacing the heart so that way everything is synced and everything functions very smoothly. So we have the SA node, which is also known as the sinoatrial node, and it's known as an intrinsic pacemaker, and it initiates electrical signals which stimulate the muscle contraction in the atria. So in each of the atria, this SA node will basically signal to the atria when to contract and when to relax. Same thing with the AV node, which is the atrioventricular node, and it's an electrical signal that passes from the SA node to the AV node, and it causes the ventricles to contract and pump blood out of the heart. So we have the SA node, which signals the instructions for the atria, and the AV node, which signals instructions for the ventricles. So these nodes are very, very important, and it ensures that the beating of the heart is very rhythmic. We want it to stay rhythmic so that way everything within the body functions very smoothly. So if someone has a malfunctioning SA node or an AV node, you will see that they do need to get that fixed and will get an artificial pacemaker, which basically paces the heart in place of anything that may be malfunctioning. So specifically, Victoria stated for us here that the pace of electrical conduction of the heart is regulated by signals from the medulla in the brain via nerve fiber. So the medulla in the brain is an involuntary portion of our brain, which means we have no control over it, and it signals when the SA node and the AV node should initiate these electrical signals that we are talking about. So with help from the medulla, we can kind of see that everything in the body has a distinct purpose, and each of these systems are working together to ensure that you are working properly. So now we have heartbeat and heart rate. So you'll see that the heartbeat cycle will basically discuss the diastolic phase and the systolic phase that we will talk about later in terms of blood pressure. So in the systolic phase, you will see that ventricles contract during this phase, and the AV valves close and the semilunar valves open. What this means is that the ventricles will push blood out, and in doing so, the AV valves will close. These are the valves located between the atrium and the ventricle. So this valve will close to prevent the backflow of blood back into the atrium, and the semilunar valves will open, and these valves are into the blood vessels that leave the heart. So the ventricles will pump blood into the arteries that leave the heart, and that is known as the systolic phase. And then after that happens, we will see blood return to the heart. So the ventricles are relaxing during this diastolic phase, the AV valves will open, and the semilunar valves will close. So once the atria collect this blood, the AV valves will open, so the valves between the atria and the ventricles will open and allow blood flow into the ventricles, and the semilunar valves will close to ensure that none of this blood is going into the blood vessels just yet. And then cardiac output is a specific term that medical professionals use to determine the amount of blood pumped out by the heart in 1 minute. So that will have your heart rate, which you can calculate by yourself, over your stroke volume. And now we have our circulatory specific terms. We have the pulse, which is the amount of heartbeats that you will hear per minute. Blood pressure, the amount of pressure exerted on the inside walls of blood vessels. So basically, within your arteries, you will know your blood pressure, as the surges from your heart will be pushing through these vessels, and you can calculate that. You need to make sure that you have a very healthy blood pressure, because if cholesterol or fat builds up within your vessels, the blood pressure will raise, and that is very, very unhealthy for you, because it will take a lot more effort for the ventricles to pump out blood to the rest of your body, since it's a lot tighter of a space. And then we have systolic pressure, which is the pressure exerted on the inside of the blood vessel walls when the ventricles contract and pump out blood. So that's the systolic pressure, which is specific under blood pressure, and the diastolic pressure is the pressure exerted on the inside of the blood vessel walls when the ventricles relax and fill with blood. So this is going to be during the time when the AV valves open and the semilunar valves are closed, like we talked about in the heartbeat cycle. And to calculate your blood pressure, you will see that blood pressure is the systolic number over your diastolic number. So if you ever go to the doctor, they will calculate your blood pressure, and a very common basis foundation blood pressure number that you will hear is 120 over 80, and that is used as a guideline to determine if your blood pressure is regular or a little out of the norm. Now we have our blood-specific disorders. So now we have leukemia. Unfortunately, this is a cancer that is very, very common within children. And it is a cancer that entails the uncontrolled production of non-functional or mutated white blood cells, which are sent to the blood in large numbers. And there are very, very different forms of leukemia. But this is basically just the overproduction of malfunctioning white blood cells, which is very, very unfortunate for people with leukemia. So it's basically the overproduction of white blood cells that are either mutated or not functioning right. Autoimmune diseases that are very circulatory specific are the juvenile diabetes, which is specific to the pancreas, rheumatoid arthritis, which are the joints, and multiple sclerosis, which are specific to nerve cells. So autoimmune diseases of the blood and the circulatory system is when the immune system fails to recognize the person's own bodily cells and attacks them because they believe that they are foreign pathogens. So the white blood cells will attack the body's own cells. So with juvenile diabetes, the white blood cells will attack parts of the pancreas. With rheumatoid arthritis, the white blood cells will attack joints and the cartilage between joints. So it's a very, very painful autoimmune disease, and it may even cause the erosion of the joints over time. And then the multiple sclerosis attacks the nerve cells, which is very, very dangerous, just like all of these disorders. A heart attack, also known as the myocardial infarction, or the MI, is the death or damage of cardiac muscle tissue due to insufficient amount of blood flow to the heart. So, causes of this heart attack may include blood clots in the coronary arteries, slow heartbeat, and the angina pectoris is chest pain associated with a heart attack. So if you do have this specific type of chest pain, it is a large indicator that a heart attack is coming on. And so a coronary artery bypass graft is a treatment for any symptoms of the heart attack, which you will see is very, very specific to the blood clot in the coronary arteries. So if you have a blood clot in your coronary arteries, this will cut off blood flow, which will cause insufficient amount of blood flow to the heart muscle. And the coronary artery bypass graft is also known as the cabbage, and it is a very common treatment for impending heart attacks. Now we also have a stroke, which is also part of the nervous system, which is also considered a nervous system disorder, but is the damage to a portion of the brain caused by decreased blood flow to a certain area of the brain, and it is caused by a blockage or rupture of the cerebral blood vessel. And the effects depend on what area of the brain is oxygen deficient. So when a patient has a stroke, if the right side of the brain is oxygen deficient, the left side of their body will be temporarily paralyzed or will be negatively impacted. Same thing goes for the left side of the brain. If the left side of the brain is oxygen deficient, you will see that the right side of the patient's body has been negatively impacted. So it's more of an inverse impact. If one side of the brain is impacted, the opposite side of the body will be negatively impacted. And then we have hypertension, which is a lack of homeostasis. And this disorder is a result of high blood pressure. So you will see that a blood pressure of 140 over 90 or higher, stress, cholesterol buildup, and high sodium can all be causes of this persistent high blood pressure. So we need to make sure that we're eating right, we're leading healthier lifestyles, so that way we can prevent high blood pressure and hypertension in turn. So that is the end of the circulatory system. If you have any questions at all, please make sure to contact us at our email located on the Contact Us page. I hope you guys have a great day, and study hard, study well, make sure to stay stress-free, and we will see you back here at Anatomy Academy. Thanks, and see you later.